So my name's Josh, and I'm a data scientist from StarCount, and I've been working there for the last couple of years. At StarCount, our goal is to basically try and understand what people are passionate about in their real lives. What do people love doing in their spare time? And we do this by looking at social media data. So over the last couple of years, we've developed a range of tools using Python to analyze social media data and get social media data. And this talk is really about the tips and tricks that we've got along the way that we just want to share with you guys. So first, social networks. So this is a visualization by an Argentinian data visualizer artist of just people retweeting each other on Twitter, and this is actually based on real data in a community. All I'm trying to do is convey with this video is that social networks are quite difficult to understand and to get a grasp on what is the overall picture of what's going on. What is the overall picture of what's happening in the social network? So the way that we do it at StarCount is we identify special types of people on the network or on the graph, and we call these stars. So these stars could be like a traditional famous person, like an actor or a pop star, an artist, or it could be an online star like a blogger or a vlogger or a YouTube star, but it could also be an influential institution such as a brand or a company. So we call these stars, and we've identified these stars across all the different social networks, and we found there to be around 200,000 in the world across the major networks. So that means there's basically like 200,000 sort of famous entities in the world, which is quite cool. So we've identified all these stars, and the way that we understand the social network is about how people interact with these stars. And by doing that, we can then understand people's passions on the social network, what people are really interested in, on a scale that's really never seen before. So this is the data process that I'm basically just going to go through today. So you start off in the web, and we download data, and then we do various things to it. And I'm basically just going to highlight four packages, Python packages, that we use along the way, which is Pandas, Twisted, Cython, and Scikit-learn. So I'm going to start off with Pandas, which is really the glue that keeps our whole process together. I'm sure many of you are already aware of it, but I'm just going to highlight it anyway. So before Pandas, there was the built-in CSV module in Python. So in this example, I'm really simply opening up a file, iterating through it, and attaching the information to a list. And this is really incredibly slow. If you do the same thing in Pandas, it's slightly different. So you read the whole file at once into memory, and then you operate on it usually in a sort of vectorized fashion, which is just a hell of a lot faster. There's no reason really anymore why you ever want to use the CSV module. The only reason which I could think of is if your original file doesn't fit into memory. And there's this really nifty feature in Pandas where you can basically chunk your file, your input file that you're reading in. So you don't have to read in the whole thing at a time. You can read in bits at a time and then operate it on the bits at a time and then iterate through the chunks. So that's a really, really nifty feature.
Is the other screen not working?
No, it's not working. Sorry. Can you see if I stand back further?
Yeah.
Yeah.
I'll try to play with it in the meantime while you speak.
I don't think they got it working yesterday.
It used to be a remote. No, it was working for a while. But, yeah.
Okay. So in Pandas, yeah, really simple SQL sorts of operations like joins and group bys are really, really quick if you use them in the right way. But another really, really cool feature of Pandas is that it supports the HDF format. So the HDF format is this optimized format for numerical data, which is the sort of data that we use quite a lot. and it's really, really good for really, really large tables. So in this example, in this table, I've got a CSV, which originally the read time was around half a minute, and then if I convert it to HDF format, the read time is in half a second, which is a ridiculous speed up. And additionally, because it's not CSV, it's not being dumb about the way it's saving the data. It's saving the data as actual numbers when it knows it's a number. You get this natural smaller size on disk. And what's also really good about Pandas is that you can do on-the-fly decompression of files and HDF files included. So you can compress your HDF file to get an even smaller size on disk. I mean, you get slightly longer read time, but it's still quite acceptable. So for our type of data, and for a lot of data I assume you guys will be working with as well, this format is really, really useful. So that's all I got to say about Pandas. Now I'm going to talk about data extraction. So for us, data extraction means basically getting data from the social network APIs like Twitter or Facebook. And the way that the APIs are structured is that you can only obtain small bits of information at a time. You can only query small bits of the graph or small bits of the network at a time. Now, if you want to understand large parts of the network, it means you're going to have to send off lots and lots of queries. And you're going to have to send off lots of requests across the whole graph. And that's the limiting factor in this part of the pipeline. This was the problem which we incurred. So our first application for obtaining data was very simple. It was just sequentially going through each query that we wanted to do in a sequential order, one after the other. Now this took ages because it's waiting upon the server most of the time to respond. So the application was I/O bound due to the server response taking a while. So the next iteration of our application was basically just to multi-thread the application. So each thread is doing exactly the same thing as the previous application. It's got a list of requests that it wants to do, and it's just firing them off one by one and doing the requests. Again, we came across some problems with this. So it works at first. Let me show you. It works at first, but then you start to get into some problems. So when you first start increasing the threads, you get a nice linear response, which is what you want. More threads, more data throughput, so you can download at a time. But then you start to get to this leveling off of throughput, and we found this to be at around 200 or 300 threads. So we were getting a reasonable amount of downloaded data, but we needed to get more than this. And we think the reason due to this is due to maybe multiple problems. One of them is that each thread is still opening up an individual connection to the network. So each thread is still doing its own activity, and also each thread is still blocking itself. It's still pretty stupid and blocking itself. Additionally, as you probably know, there's the GIL in Python, so you're not really getting true parallelization between all the threads. So the way we solved this was basically to use asynchronous framework, and the asynchronous framework which we used in Python was Twisted. So synchronous programming is basically what I just described in the first application. It's when you've got one task after the other and you're just executing them. Then you've got parallelized programming, so where you just do all of them in parallel. But at asynchronous programming, you're being a bit more clever about things because you know that you're being blocked by the server. So when you know you're being blocked by a server, you go do another task. So you chop and change between the tasks, being a bit more efficient of your CPU time that you're using, instead of just waiting upon the server to respond to you. Now, like I said, so we use Twisted to do this in Python. There's a few other frameworks as well. Twisted is generally used for building custom servers. So this is a slightly different use case than what it's usually used for. Because you've got this chopping and changing between the tasks, you're going back and forth between the tasks, the flow of your program is broken up quite a lot, and it makes writing asynchronous programs quite different and difficult compared to writing normal programs. And we found there to be quite a large learning curve with using writing these programs and using the twisted framework. So here are just some tips for what we learnt, or what we should have done in hindsight, if anyone is going to take on a similar project. Firstly, I would read a book beforehand and go through all the exercises, which is obviously not what we did. We jumped into the deep end. And I particularly would recommend this free book that's online by David Petrocolas. And there's exercises and it's really good, and you just read it and you'd get a lot better understanding about how to use twisted. Also, debugging is quite difficult and different to normal programming because like I said before, your flow is broken up quite a lot. It's quite difficult to see where your bugs are starting out and how they propagate through the program. So in the end, we ended up visualizing a lot of our program using flowcharts, and we found this to be really, really useful as well. So even though it was difficult, the result for us has really paid off. Now we've got this sort of task server that sits in our local network that dishes out tasks to clients in the cloud. And we've got these clients that are in the cloud that we can scale up and down. Each of the clients is sort of its own asynchronous application. And this allows us to fine-tune how much bandwidth we want to use at that particular time and how much data throughput we want to get. And this essentially allows us to linearly scale up and down the data throughput that we want to get at any particular time. So in the end, it was really useful. It's a really good exercise. Okay, so next is data mining. So once we've got our data, we want to do something to it. In this section, I'm going to highlight Cython and how we use Cython to optimize the particular data mining task. So I'm just going to explain first what we were trying to optimize, and then sort of show you the iterations that we did to optimize the task. So, like I said before, we use stars to understand the social networks and how people interact with these stars. If we just consider the interactions between the stars on the social network and the users or followers, then we've basically created a bipartite graph of the network. So there's two types of nodes, and we're only considering the interactions between the followers and the users and these influencers on the network, the stars. And because we've created a bipartite network, we can now start thinking of the stars as just basically groups. They're defined by the groups of followers that follow them, or they're the groups of users that follow them. And that's so we can start thinking of them as basically sets. And once we start thinking of them as sets, we can start doing set operations between different stars to determine different things. So for example, if we want to see how similar two stars are, one of the sort of things we could do is look at the overlap of the people that follow both of the stars. Or another thing we could do is look at the Jacquard metric. So the Jacquard metric is a general metric for describing similarity between sets. And in our case, it would be 0 when there's no overlap of users or followers, and it'd be 1 when they're exactly the same set. Now, the Jacquard metric is really useful, but it's really expensive to compute. It's sort of an n-squared problem. So a technique to get around this is by using the min-hashing algorithm or min-hashing technique. So what the min-hashing technique does is you've got this set. For example, here we've got a set of stars, and you basically compress this set into a vector of fixed length. So here I've got a vector of length 5. And you've compressed all this information into this fixed length vector, and that's an n. That takes n time, so that's cheaper than calculating the Jacquards between the sets. And once you've got this vector, it's really, really cheap for you then to calculate the Jacquard between two different stars. So this vector you also call a signature. So you calculate all these signatures of all different stars, and then to be able to approximate the Jacquard between these two stars, you basically identify the values which are in the same place and are also the same value. So here 4, 2 and 9 are in the same position and the same value. So there's 3 of them, and then you just divide by the length of the vector, which is 5. So the jack-odds in this case between these two stars would be 0.6. So that's obviously a ridiculously cheap operation. It's just really simple vector maths. And the expensive bit is to create the signatures in the first place, but that's still cheaper than directly calculating jack-odds between stars or between sets. So it is only an approximation, but it's a good enough approximation for our purposes. So there's multiple ways of calculating these star signatures. So this is the data mining bit, calculating these signatures. And the way that I'm going to be doing in the next few slides is basically for each of the users on the network, or the followers, we need to collect... Oh. Sorry. For each of the users on the network, we need to collect all the stars that person follows. Oh yeah, thanks.
Can I ask a quick question on the maths whilst we're here?
Yeah.
So right now you're taking a length of 5, but what if one star set had like a length of 6 and the other one had a length of like 4, for example? What would the underlying number be?
So
5.
So the point is you compress all the... So the question was, here the vectors are a length 5. What happens if one of them was 6 and one of them was 4 or something like that, or different lengths? The point about this technique is that you compress any set into a fixed length vector, so they're always the same length. So in this example we used 5, but that would generally just be too small, so you'd use something like 100. But so you compress, no matter how big the set is, this is what's really cool about the technique, no matter how much the set is, you're compressing it into this fixed length vector. And then you just do that simple operation to get the jack-odd between the two sets. Calculating the signatures from the stars isn't actually that difficult. The maths behind it isn't that difficult. I just don't have time to explain it here. But if anyone's interested in it, there's lots of really good resources online on how to explain it. Yeah, so for each of the followers or the users on the network, we basically need to collect all the stars that person follows. We then hash, in some sort of way, the follower ID. And then these two pieces of information we feed into this function called update star signatures, which basically somehow creates these star signatures once we've done it for all the fans. So this is kind of like the number crunching bit that we do. So this was our first iteration of the code, whereby we've got this edge list. So the edge list is basically a file which just details what star each fan or follower follows, what each user follows. And we go through this edge list and we basically collect for each of the followers all the stars they follow, and then we do this hashing process, which is here, and then we update star signatures, and this is sort of the number crunching bit. So the important bit is that we've also got two other things going on in this for loop. We've got an if statement because we have to discard certain types of followers, and we've got this dictionary lookup to convert a star ID into an index, which is later used in a matrix. But that's not important. The important bit is that I've got this if statement and I've got this dictionary lookup, and this, as you can imagine, was incredibly slow because I'm iterating through a CSV line by line. So our second iteration was quite simply just to use Pandas instead. So we read in the whole edge list file in once, which is about 1 billion lines long. And also, I've converted it into HDF formats, like I mentioned before. So it's a lot quicker to read in. Additionally, I've moved the two statements that I just spoke about and sort of vectorized them and moved them out the for loop. So I've got that if statement, which I moved out the for loop and vectorized it, and I've got that dictionary lookup with converting the star ID to an index, and I moved that out of the for loop, and that's basically just a table merge when you vectorize it. So I've tried to keep as little in the for loop as possible because that's being executed about 1 billion times. So just by doing those two simple changes, we've got a really good speed up of nearly a half. So the next iteration was to basically use Cython. Now, Cython, if you don't know, is basically like a hybrid language between Python and C, and it gives you all the flexibility of Python when you want it, but it also gives you the rigidity of C when you also want it. So I think it's really good because it means you don't have to leave the sort of Python mindset, but you can sort of, in a pseudo way, write C code. So it's the same. It's a superset language to Python's nearly. So you've got it's pretty much the same as Python, but you've got these extra declarations which allow you to declare types and a few other things. So in this example here, it's pretty much exactly the same for loop, except at the top, I've just added in type definitions in the Cython language to declare the types of the inputs and output variables and the variables in between. So that gave a modest speed up. So before it was on about 11 minutes, now we're on about 10 minutes. So it's not a huge speed up. But where you get the really, really big speed up is when you start to remove the Python objects out of your Cython code. So certain operations on Python objects in Cython means the Cython has to communicate back to the Python virtual machine, and that process, as you can imagine, is quite slow. So you want to pretty much completely separate your Cython code from your Python when it's being executed, and then it sort of outputs back to the Python virtual machine at the end. So the two things that I've removed here you can see I've got this list on the left hand side called follower stars, and I've just, instead of using a list, I've used a C array, a fixed length C array. I've also got this Numpy array which I'm declaring, and I've also just created a C array instead as well. And because I've basically because I've taken out all the Python code that's going to be calling back to the Python virtual machine, then you can actually release the GIL here, which is really useful in some situations, although in this situation wasn't that useful for us. So the way you can determine what code is slowing up your Cython program is there's a really nifty feature on the command line. So the tool that you use is this Cython command, and then you do -a, and it basically says annotate, and then it outputs a HTML file, and then it annotates your code, where's slowing it up and what's talking back to the Python virtual machine, and that's really useful because then you can go through and then make the changes and speed up your code. So that, so I also added at the top some compiler directives for Cython. So I've just added all these just to improve performance basically. So the first one is turning off bounds checking. So that's basically saying don't check my indices to see if they're out of bounds of vectors or arrays. I've also turned off wraparounds, so that's to do with negative indices, and I've also said UC division instead of Python. So all these improvements had a dramatic speed increase compared to what we had before. So before it was on 18 minutes, now it's on 3 minutes. So these are all the iterations. So the first four are the top four that I've just shown you, and the last bar is an iteration which I haven't shown you, which is the iteration where we've actually optimized the number crunching bit of the min hashing algorithm. So us doing that optimization of the min hashing algorithm only actually gave us a speed improvement of about a minute, which is incomparable to the other speed improvements we got from doing simple things by using Pandas and by moving to Cython and removing the Python code, which doesn't have that much sort of time expense for doing those things. So the lesson learned for us was that you shouldn't assume what's slowing up your code, because when we first approached this problem, we basically thought that the hardcore number crunching bit of the min hashing technique is going to be the bit that's consuming most of the time of the program, but actually in fact it was just all the logic that went around this. So you really should profile your code to determine what's slowing up your code and what's making it go slow. And what's really good nowadays is or what's really good is you can now use IPython for this sort of thing. So IPython have got two really good magic commands like normal profile, which is like function profile, and line profile, which profiles the lines in your code. And using these two tools, you can really determine what is actually slowing up your code and what you should spend your time on improving. What's also really, really cool is that you can actually now paste Cython code directly into IPython. And it does all the compilation steps for you. So Cython, usually you have to convert the Cython code to C and then compile the C library, and then you import that into your Python module, or import the module into your Python code. But Cython, IPython allows you to paste Cython code directly into the console. It does all those steps for you, and then you can use the Cython function like you'd use any other Python function, which I find really useful. And also, in the IPython notebook, you can do this -A, which is what I was talking about before, which is annotate. So if you do -A or --annotate, then it generates this output and it highlights the areas which are slowing up your code and talking back to the Python virtual machine. So it's all really easy to do this in the IPython console. Okay, so that's all I got to say with data mining. Now I'm going to talk about data enrichment with Scikit-learn.